All right, so another cool thing we can do with alcohols is we can turn them into good leaving groups, make them more electrophilic, and then do substitution or even elimination reactions. So remember, by itself, the alcohol group OH is not a good leaving group. So having a mechanism like this is going to be a big no-no. The OH is not going to leave. Remember, to have a good leaving group is you need to be for it to be stable by itself. And so generally good leaving groups are conjugate bases of strong acids. OH is the conjugate base of water. Water, obviously not a strong acid. So think back from first semester organic chemistry. One of the main things that one of the things we learned to do with alcohols was tosylation. And so what we can do with alcohols, say that we have this particular alcohol right here. What we can do is add some tosyl chloride. We abbreviate that as TSCl with some pyridine. And what we're going to do is switch it from an OH to an OTS, where the TS stands for tosylate. And then you could add some kind of really good nucleophile. And then you could do some kind of substitution reactions, right? Do an SN2 type of reaction to switch the stereochemistry here, right? So remember, OTS is a tosylate group. Right, coming from the name toluene, right? And then we have this sulfate group on the end there. So that's one way you can make it into a good leaving group, is to tosylate it. Another way to make it into a good leaving group is to just change it into an alkyl halide. So we can go from alcohols to alkyl halides relatively easily as well. If you've got a tertiary alkyl halide, tertiary alcohol, you can just add some HX to it to turn it into the alkyl halide. Don't forget that this will racemize the compound because we go through a carbocation intermediate, right? This is through an SN1 type of mechanism. Let's just go ahead and go over the mechanism real quick in case you forgot from first semester. We'll use HBr here, right? First thing, our alcohol is going to act as a base and pick up that H+. At that point, we formed water. Water is a good leaving group. We can form a carbocation intermediate. And this, of course, is where you have to be careful, because anytime you have a carbocation intermediate, you can have rearrangement occurring. In this case, if it's a tertiary alkyl or alcohol, it's unlikely to happen. And then we just have our halide attack. In this case, it's bromine, and add on to our compound. And of course, these alkyl halides are good leaving groups. So then we could do some kind of nucleophilic substitution, or we could do something else with this, maybe some elimination reactions or whatever you want to do. If you have a primary or secondary alcohol, then what we can do to transform them into alkyl halides is use specific reagents. So for example, SOCl2 with pyridine will switch the alcohol into a chloride, and as well as inverting the stereochemistry. And similar scenario with PBr3, we're going to switch the alcohol for a bromine and invert the stereochemistry. So here's the mechanism for both of these. Overall, they're relatively similar. So there's our SOCl2. What we're going to do is have our alcohol act as a nucleophile, attack the sulfur, break this sulfur oxygen pi bond. Don't forget all of your charges. It's easy to forget some of these charges. And then what this oxygen is going to do is reform our pi bond and then kick off the chlorine. The pyridine in solution, which looks like this, can then deprotonate our alcohol to give us a neutral oxygen back. After that, we can then have our chloride come in and do an SN2 reaction, right? So the chloride is going to attack this carbon attached to the oxygen, and then this carbon-oxygen bond is going to become a carbon or an oxygen sulfur double bond, and the chlorine leaves. And so at this step right here, this is where the inversion occurs. Right, we're doing an SN2 reaction, so we have inversion of the stereocenter. So then we have our alkyl halide, some SO2, and some chloride floating around as well. The mechanism with PBr3 is approximately the same thing. Our alcohol acts as the nucleophile, attacks the phosphorus, kicks out a bromine. And then we simply have our bromide come in and do an SN2 reaction as well. And so in this case, this is where the inversion would occur. In this case, we don't have stereochemistry, so we don't have to worry about that. But then there's our product. So you can see we have kind of two really good ways of making them into good leaving groups, right? Either tosylation or straight up just switching it to an alkyl halide. The effects on the stereochemistry of the compound are a little bit different. So for example, if we take this alcohol here and then we tosylate it, right? When we just tosylate it, we don't change the stereochemistry. And then if we were add some kind of good nucleophile, we would do an SN2 reaction and we would invert the stereochemistry. The other way to do it is to change it into an alkyl halide. So I'll do PBr3 here. Here we invert the stereocenter right away. And then when we add a nucleophile, it's going to invert yet again and thus go back to its original configuration, right? So depending on which of these two pathways you choose, you can either retain or flip the stereochemistry of the compound.